Okay, we finished this numerical example about current transformers, the performance analysis using the per unit CT error and the ratio correction factor. Okay, I would like to say that please remember to visit my GitHub repository, and there you will find the live script file, MATLAB live script file that you can use to follow all the numerical calculations, and if you want to try making changes on the input data and improving to see the changes, please feel free to do it. Okay, remember, go to the GitHub, my personal repository about power system protection, and you can download this file and you can see all the numerical results. Okay. Now what I want to do is I would like to move from this example. One of the key points here of this example is that we consider the magnetizing branch as a constant. Any one of you that is familiar with magnetic circuits and somebody that took a training about electrical machines, you must remember from magnetic circuits that the magnetic core has properties, and one of these properties is basically the non-linearity between current and flux in the magnetic core. What I will do now is move to the next topic. Okay, the next topic is, okay, we need to be more realistic in terms of the magnetizing characteristic of the current transformer. Okay, as I say before, the magnetizing branch is not constant, and to be honest is something a bit more complex that is not a constant. It's not a constant, but also is non-linear. In real life, the magnetizing branch is not constant, instead depends of this characteristic that is called the magnetizing characteristic of the current transformer. Here you can see that this is the secondary voltage. This is the secondary voltage at the current transformer. Here we have the secondary excitement current. This is the magnetizing current, and on the right hand side we have different current ratio. Okay, if you remember two winding transformer, this curve over here resembles the magnetizing curve of a two winding transformer. But what is the most important consequence that this non-linearity between voltage and current? Well, the first consequence is the magnetizing branch is not constant, but at the same time, and very important, is that the performance, steady-state performance of the current transformer is also not constant, and it starts to be a bit more complicated. Okay, if you have time, please go and check the IEEE standard 6C57, and you can see the basic requirements for the instrument transformer. In this case, this curve over here showing the secondary voltage and the secondary exciting current is taken from the C57. And also, if you have time, also I highly suggest that go to the IEEE 242, that many of my slides are coming from information of there. Okay, but here it's a typical secondary excitation curve. Okay, but in real life, you must remember that depending of how good is the magnetic material used at the magnetic core, you can have very different magnetizing currents. Okay. Typically, when we are talking about current transformer, we can identify two different type of current transformer. Some current transformers used for measurements. That is the, let's say, low quality magnetic material used to create the magnetic core. One of the idea is that for measurements, we need linearity for measurements range. I mean, between 0 and a normal overload, probably 1.2 or 1.5 times the rate current, we need a linearity. And then if the current go to full current, well, we use the saturation on the secondary exciting curve in order to avoid the destruction of the measurement device. For that reason, when we use the class M measurement class for current transformer, we are talking about current transformers that they are very good for reproducing the signal, primary signal on the secondary, but mainly in a regime or a class that is related with around the nominal current. But on the other hand, the protection class transformer, and that is what we call the type P. The type P is a bit more expensive because the protection transformers, they must be able to reproduce in a proper way the rate current on the secondary, but also if there is a fault, we need to keep tracking how good, we need to keep tracking in a good quality the signal from the primary side. As a consequence, the magnetic material that we need to use must be able to be saturate a very high level of current, short circuit currents. It's typical that for normal applications of current transformer, the saturation of them is around 20 times or 30 times the primary current. And what is very important is we need to take in account that sometimes there is DC offset inside the short circuit current, but we need to be able to reproduce this behavior in terms of the wave form of the fault current without including saturation or phase angle error. Okay, something that is very important, all my students must be familiar. We want that the signal on the secondary must be the same on the primary, just change in magnitude. But phase angle error is something that can happen. Okay. The current transformers, they are standardized. What I'm trying to say is, if you need to buy or you need to specify a current transformer, they are very specific transformer ratio. In this case, I am presenting a couple of tables taken from the Holowitz and Park book, but as you can see, the secondary winding is mainly 5 amps, and that means those CTs are used in America. Also here, they are more transformer ratio, standardized transformer ratio. If you want to see the full table and get more information, please feel free to visit and see the IEEE standard C37.13, and where all the standard requirements for instrument transformer are presented there. Okay. Now, main conclusion here is real CTs, they are a magnetizing curve that define how the magnetizing branch change, okay? And I would like to explore with a basic example how the magnetizing characteristic affect the performance of the current transformer. And here, let's start with another American current transformer. This is 600 on the primary, 5 amps on the secondary. And we can see here we are using the magnetizing curve that is presented, and you can identify on the right hand side we are using the transformer 600 to 5, okay? It's required to calculate the current in the secondary winding of this CT if there is a primary current of 5,000 amps. Also, in this case, we know what is the burden. The burden could be the load created by the relay, by auxiliary transformers and contacts and so on. And in this very specific case, we can say that the secondary leakage impedance is neglectable, okay? Okay. What is important to know is that we need to assume that the impedance angle of the magnetizing branch is 60 degrees, and also that the magnetizing branch is not linear. In fact, it's following the magnetizing curve present here on the left-hand side. And the idea is to calculate the performance indicator, mainly the per unit CT error, and calculate the ratio correction factor, okay? Very simple. The first step is we need to transform the current from the primary size to the secondary size of this transformer. It's extremely simple. Using transformer ratio 600 to 5, we can identify the current, and the secondary is 14.66 amp, okay? Now, immediately below, you can see we are connecting a circuit, an equivalent circuit of the transformer, okay? We are injecting the secondary current. Here you can see the load representing the burden, and we have the magnetizing branch, okay? We can define the terminals A and B between the magnetizing branch, and because we don't know the magnetizing branch, but what we need to do is we can apply a Thevenin equivalent model. The Thevenin equivalent model for that circuit is presented on the right hand side. You can see terminals A and B, and you can see the magnetizing branch. The Thevenin equivalent model is very known because you have an ideal voltage source with the Thevenin voltage in series with the equivalent impedance, okay? However, here is extremely simple. The Thevenin voltage is the open circuit voltage, is multiplying this current by the burden, and the equivalent impedance is also very simple, is equivalent to the burden impedance, okay? Now we have here our Thevenin equivalent model, and we know that the the magnetizing impedance is a complex number in polar form, and we know that the angle of the magnetizing impedance is 60 degrees, okay? What I did here is just transform this polar form into rectangular, okay? And then, using the Thevenin equivalent model, we can say that the magnetizing current is calculated by the Thevenin voltage divided by the total impedance. In other words, to calculate the magnetizing current, we divide the Thevenin voltage by the series of the magnetizing and the burden. Okay, what is interesting here is we know the Thevenin voltage, we know the total burden, we know the angle of the magnetizing branch, but the unknown variable here is the magnitude of the magnetizing branch. Okay, but it's very simple to see that the voltage on the secondary of our current transformer follow Ohm's law. What I'm trying to say is the magnetizing voltage is equal to the magnetizing impedance multiplied by the magnetizing current. As you can see, now this equation here and this equation here, we can combine both of them together, and then we will get a simple equation that have as unknown variable the magnetizing currents. Okay, using the Thevenin equivalent model, we arrive to this circuit where the magnetizing branch is located between the points A and B. Now, what we need to do is use this circuit to create an equation to calculate the magnetizing branch. But taking in consideration that the magnetizing branch has an angle of 60 degrees, okay? It's very simple to define the equation defining the current using the Thevenin equivalent model. Is very simple. Using Ohm's law is the voltage supply, Thevenin voltage, divided by the total impedance. The important factor here is that the magnetizing branch provide a complex number because the magnetizing branch has a 60 degree angle. On the other hand, the voltage across the magnetizing branch is what we know as the magnetizing voltage, and this magnetizing voltage is calculated using basic Ohm's law. Okay, now we have equation 1 and equation 2. When we combine equation 1 and equation 2, we realize that we have a very interesting problem, because in equation 1, the unknown variable is the magnetizing current and the magnitude of the magnetizing impedance. But on the other hand, at the second equation, the unknown variable is the magnetizing voltage and the magnetizing impedance. In this case, we have two equations, but the issue is that we have three unknown variables. Okay. One way to solve this problem is using some mathematical calculation, numerical calculation. For instance, we can change the magnetizing impedance. Here I show the MATLAB result from 0 to 100 ohms, and we can create a table, and that table present what is the magnetizing current, and here showing the magnetizing voltage. Okay, why this is extremely important? Because the next step is probably the most critical. Okay, the most critical step, because what we need to find is the real values of the magnetizing current and the magnetizing voltage that satisfy the equation the equation 1 and equation 2, but at the same time that follow the rule defined by the magnetizing curve. In this case, in yellow color, you can see here in yellow color, what we did is we took the values from the table, and the yellow line is an approximation of plotting the results for different magnetizing impedance. And then what we did is intercept the magnetizing curve of the transformer 600 to 5, and we found that intersection is at 17 amps and 260 volts. This is a method that is one way to solve the problem, because the situation is that we have a specific equation to define the magnetizing current and the magnetizing voltage, but who is defining at the end how the voltage change when the current change is the magnetizing curve. That is the reason for using this approach, okay? But now let me come back again, and now let me calculate what is the performance of our transformer if we assume that the magnetizing branch, imagine now that we say, okay, the primary current is 14.66 amps, okay? If the primary current is 46.66 amps, we can use the equation number 1 and calculate what is the magnetizing current. If we know the magnetizing current, now we can estimate, because we know the current here I1, we can use Kirchhoff current law and calculate the current I2. And here we can get the current I2. What is the idea now? Well, if the voltage is 260, as we got before, and now the current is the current that is moving on the magnetizing branch is 17.01 amps, well, we can identify how much is the magnetizing impedance, okay? In this case, the magnetizing impedance is 15.29. However, you must be aware that this is evaluated for that very specific operating point, okay? If the current in the primary move up or down, these magnetizing impedance will change following the magnetizing curve, okay? But for this calculation, we show that this is the value, the operating value at that very specific current, okay? But now that we know the primary current, 41.66, now that we know the magnetizing current, 17 amps, well, the final step is calculating the per unit current transformer error. And using the basic definition, we obtain here per unit CT error of 0.40, okay? And then we can calculate the ratio of correction factor, and in this case we can identify that the resultant ratio correction factor is 1.47, okay? Again, this problem has been very, very interesting because the magnetizing curve defining the relation between the magnetizing current and magnetizing voltage, that create the nonlinearity. And nonlinearity means that we need to identify properly the operating point. But the problem is that we don't have an analytical equation to define the secondary voltage and secondary exciting current. If we have that equation, the problem can be solved analytically, but because here we only have the graph showing the magnetizing characteristic, we need to use this very conservative and different approach, that is the graphical method. Okay. Okay, well, that's all regarding the example of magnetizing curve in current transformer. Okay, the next step is moving forward, and now we need to talk about standard class designation. Okay, if you remember, I was talking about how you can obtain the different steady state performance indicator, and I introduced two of them: per unit current error and the letter R, that is the corresponding ratio correction factor. Okay, but the ratio correction factor and the per unit CT error, they can be calculated using some assumptions as I presented before, but that is only if you have the magnetizing characteristic. If you have the magnetizing characteristic, it's always possible to calculate the performance of your CT. But if you don't have it, that is where we need to start to use the standard class designation. Okay, the American National Standard Institute, ANSI, and the IEEE, they create a designation for letters C or T. The letters C or T, they are used to define the performance, the class designation of the current transformer. For instance, you can see a current transformer, and you can see the indication 10C400, or you can see 10T300. Well, what you need to understand is that this is a code. This is a code based on the IEEE standard, the C37.13. In this standard, we say that the first numbers, the first integer, in this case the 10, describe the upper limit on the error when you are using your CT. Okay, and this error is defined when the voltage on the secondary terminals is equal to the second integer presented on the equation. And at that moment, it's happening that the current in the transformer is 20 times the rate value. You must remember, it's very simple. For instance, the case 10C400. In this case, the error is the upper limit of the error is 10% when the voltage and the secondary winding is 400 volts, and that is happening when the 20 times the nominal current, typically 5 amps, is moving across the secondary of the transformer. Okay. I will explain a bit more in the next slide. What you need to understand is first that the letter C corresponds to when the performance of your transformer is calculated, and T is when we use tests in order to determine the performance of the transformer. What is really important? What is really important is that C or T, both of them define the secondary voltage. The secondary voltage in the case that is moving 20 times the rate current. Okay. You must be careful. Standards are there. Okay, standards are there. However, you must be careful about the standard, because IEEE standard and IC standards, they are quite popular in the ANSI. IEEE is quite useful in America, and IC quite useful in Europe. However, you must be careful because, for instance, between standards there are different definitions and different numbers. For instance, if we are talking about the Australian standard 1675, or the IC standard used here in Europe 61869. If we have a transformer and this current transformer is 10P400, in this case we must understand that the first two digits represent the accuracy. I mean, what is the maximum error? 10%. And in this case, 400 represent the voltage that is driven on the secondary when you have 20 times the nominal current. Here there is a better example. For instance, the classification, the class designation is 10C400. In this case, the first two digits represent the accuracy. In this case, we are saying that there is an error with the top limit, the upper limit 10%. C, because this performance is calculated, and 400 represent that they are 400 volts when the secondary current is 20 times the nominal. In this case it could be 100 amps. Okay, here there is a short example. Let's see this small example, very simple. Again, we are using an American current transformer 600 to 5. And in this case, we can see that the transformer class is 10C400. Okay, this current transformer, there is a primary current, nominal primary current of 5,000 amps. Okay, well, as you must be aware, the current at the secondary of this transformer is 100 amps, and when there is less than 10% error and the voltage on the secondary is equal to 400 volts. Okay, remember, this is coming from the definition 10C400. That means there is then less than a 10% error when we have 20 times the rate current on the secondary. I mean, 20 times 5 is 100, and the voltage is 400. Okay, what we are doing now is calculating the magnetizing impedance. To calculate the magnetizing impedance is very simple. We can define using Ohm's law. The Ohm's law in this case is the voltage on the secondary divided by 10% of the current on the secondary. When you put the number together is 40 ohms. Okay. Now what we are doing is referring the nominal current from the primary, 5,000 amps. We use the transformer ratio 600 to 5, and we obtain the secondary current, and that is 41.66. Okay, if we assume that the maximum error is 10%, we are talking about that at any moment the discrepancy, the maximum discrepancy, could be 4.166 amp. Okay, now what we need to do is very simple. Now what we need to do is, okay, the maximum voltage at the secondary when we are using the the 20 times the nominal current, at that moment we are talking about a 400 volts voltage across the secondary of the winding, the secondary winding. Now what we are doing is basically using the this voltage 167 in order to define what is the maximum burden that could be installed in this transformer. Well, and the maximum burden is very simple. We have voltage and we have what is the minimum current that we can have when the voltage is maximum, and in this case we have the maximum current should be 41.66. But if we have 10% error, and in this case 10% error below, the current is reduced by 4.16. And if the voltage is 167 using Ohm's law, this gives us the burden, the maximum load, the maximum impedance that you can, the minimum impedance that you can install in this current transformer. Okay. In this case, I must be honest, this very specific example, we are assuming again that the magnetizing current is in phase with the secondary current. That is the first assumption, and that is not necessarily true. Okay, that is not necessarily true, but in this case we didn't say anything else, and this was the most simple way to solve this problem. Okay, I would like to include this slide because I have been I have been advised by the friends at the utilities. I am academic. I love the use of standards. Standards are very well defined, many years and many hours, working hours of a lot of clever people to develop the standards. But in real life, also people at the manufacturer companies, they spend a lot of time testing the equipment, and they know much better how the equipment performs, and based on those tests they create the application instruction, and it's very good idea. If you are in a design stage, you can use the standard, because the standard is something that will happen and is realistic. But if you are in a real power system and you are working and dealing with real protections, the best advice is that you take in account the recommendations, the instructions provided by the original equipment manufacturer. What I'm trying to say is all those famous brands, ABB, General Electric, Siemens, Cell, blah 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 blah, all of them spend many hours running tests on those equipments, and they know at the very end all the characteristic and the performance of their equipments. And for that reason, it's good idea take an advice and go inside those documents. General Electric, Siemens, ABB, etc. They have very good documents. Please try to read those documents. Okay. Now I need to move forward, and I will start to talk about something that is extremely important. As you must be aware, when we are working with currents, we need to be careful about the direction of that current. And in the case of CT, current transformers, we need to be extremely careful about the current direction. And there is a reason that there is a general establishment that say we need to include polarity marks. Okay, every single CT, there are some marks that they are installed, or they are coming from the factory, and those marks define the polarity. Okay, what is the idea of those polarity marks? Well, they define the instantaneous direction of the current. I mean, if the current is going in this way, you can identify what is the direction on the secondary if you use properly the polarity marks. At the same instant that the primary current is entering to the marked or dotted primary terminal, the corresponding secondary current, the current on the secondary, is leaving in the similar marked secondary terminal. Okay. In theory is some marking that is similar to the two winding transformer. Okay, the power transformer. The terminals are clearly identified in two different ways. One of them is using a dot, similar to the dot convention that we use for mutually coupled inductors. But also there is a classical standard that defines some markings, some numbers, and some marks that define what is the terminals. Okay, for instance, IEEE use the letter H and X to identify primary and secondary terminals, and that represent the location of the dot. That means positive current going in means positive current going out at X1. Okay, IC also have a code. In this case, for the primary P1, if the current is going inside P1 into P1, you will get on the secondary current going out at S2. Okay, it's something extremely simple. Here you can see the circuit diagram. In this case, current in H1 means current going out at S1. Okay. Something that you must be careful is those polarities define current direction. Okay, but there is a possibility that the current at the primary and the secondary have a phase angle error. Okay, this is a topic that is not covered here, but you must be aware and read the manufacturer documents and the factory documents in order to understand there is a possibility of an error at the current angle between primary and secondary. Let's go quickly. There is a small example about polarity and marks, and let's start with this. Let's consider here we have two current transformers. Of course, they are in series connection at the primary. You can see CT1, CT2. Those big dots over there represent the marks for polarities, and they are 10,000 amps at the primary. Okay, 10,000 amps, and the transformer ratio is 1,000 to 5 and 1,000 to 5. Okay. You can see extremely simple. If there are 10,000 amps in the primary, that means that 5 amps should appear on the secondary. However, what is the interesting thing here? The interesting thing here is that the current 10,000 amps at the primary is going out at the dot connection. That means that the current polarity at the secondary must going in. 5 amps here, 5 amps in CT2, and because the connection, I believe you can see over there, in this case the connection is both current transformers, they are connected in parallel at the secondary. As a consequence, the impedance low will receive 10 amps when they are 10 kiloamps at the primary winding, okay? But now let's see the impact of changing the polarity. Now let's see, we keep C2 as we say before, but now the polarity of the transformer CT1 is changed. Now the interesting thing here is that because the polarity of the current transformer CT1 change, the direction of the secondary current here now is changed again. But the interesting part is that because those transformers, they are in parallel connection, well, the total current moving at the burden, the total current moving to the load is 0, okay? This example is extremely simple, but what we want to show you here is that the selection of the polarity used at the secondary of the transformer, they can make the burden receive different current levels, okay? Okay, now moving forward, we have another section. This is the section for the transient performance of the CT, okay? Again, I must remind you that this class is an introductory level of CT and voltage transformer VT, okay? As a consequence, the transient performance, the dynamic performance here is not as deep as expected in other postgraduate levels, okay? But what is important to see is what are the basic characteristics defining the transient performance of a current transformer, okay? In a current transformer, you must remember here we have the current transformer equivalent model, but in this case, the idea is that we are using the time domain representation. You can see explicitly the magnetizing inductance, and also here one inductance representing the burden, okay? And in this case, we are assuming that we have a current at the primary. The current that is moving in the primary is similar to a short circuit current. What I'm trying to say is they are a current that is an AC component, and then we have a exponent decreasing component that is add to the current at the primary, okay? This is something similar, let's say very simplified, but looks like a classical RL energization current, okay? Now the interesting thing is we can apply Laplace transformation. And then from there we can write equation for the current, and for the flux linkage, okay? When we solve the equations, we get an equation for the flux linkage in the time domain. You can see here the exponential component and the alternating component. And here for the current and the secondary, again, we have a AC current. You can see here the time-dependent sine wave, but also we have this exponential, decremental exponential affecting the current, okay? To explain a bit more about the transient, again, this is something that we don't want to go so deep, because this is more complex, especially if you start to consider saturation of the magnetizing branch. Let's do a very basic example. Let's consider that we have a very basic burden, and this burden is a resistor, 0.5 ohms, And in this case we are using a current transformer, and there is a resistance to represent the core losses, 100 ohms, and there is a magnetizing branch of 0.005 Henry, and the nominal frequency is 60 Hertz, okay? And in this case, the primary current is 100 amps. We assume that the primary fault, I mean the decremental or the exponent that is decreasing over the time, has a time constant of 0.1, okay? Well, this is the current, the numerical value for the current, the time domain representation of the current that is moving on the primary. Then we calculate the time constant related to the CT. Here we get the two expressions defining the flux linkage, and the secondary current. Okay, here is the expression for the flux linkage. Here is the expression for the secondary current. You can put the numbers together, and you can see again there is a AC component, and in this case there are two decremental components for the flux linkage. And again here for the secondary current, you put the number together, and you can see decremental component and decremental component and AC component. Okay, now we can create a plot. And in this plot we have the short circuit current I1. You can see is the big one, and the big one is also decreasing over the time. Okay, then we have another two plots. The second plot is the current on the secondary. You can see here the current at the secondary. The current at the secondary, of course, there is a phase angle between primary and secondary. As I say before, usually we don't take in account that phase angle. At least the manufacturers say that. In the previous example we didn't, but in real life there is a small phase angle. You can see there is a very small phase angle, but it's there. There is a difference between the current instantaneous value at the primary and the secondary, and that create a phase angle. Okay, and the third plot here, and that is the quite interesting third plot, is the flux linkage. Okay, the flux linkage, before the fault, we assume there is not magnetic flux. Then when the short circuit appear, the flux start to increase, but there is a red line, a horizontal red line over there. That horizontal line represents the saturation of the magnetic core. In that case, as you can see, the saturation level is reached several times when the flux linkage is changing over the time. Okay, what we want to say is, in time domain representation, the analysis is far more complicated, especially if we include the inductance component of the burden. Okay, during transient processes, the saturation of the CT can be extremely important, and all these phenomena must be examined carefully as using time domain simulation software. Okay, in this course we are not going to do that, but the idea of this example is that you realize that the transient performance of the current transformer is a bit complicated. Of course, modern simulation software have the capability to do so. Okay, it's very important that you must be aware also about the phase angle between the primary and secondary current. Okay, It's really important that you must be aware of that, and any moment you must read the technical documentation of the equipment in order to be sure. Okay. Well, we are progressing a lot, and now I need to talk about something that is called the auxiliary current transformers. Auxiliary current transformers, they provide again a galvanic separation between the CT. Okay, but the interesting thing is, what is the idea of those CT? Okay, those auxiliary CT, they are not necessarily used for measurements. Okay, they are CT, but those CTs, they are used especially when we need to do some adjustment regarding the current circulation at the relay circuit. Okay, or if we have so many relays and the burden start to be extremely high, we can use the transformer ratio as mechanism to modify the apparent impedance that the current transformer can see. I believe all of you must remember there is a relationship between the transformer ratio and the impedance when you refer the impedance between the primary and the secondary. Okay, this property of the current transformer can be used in order to modify impedance, but also more than that, we can use also to change to shift the vectors, or also to do some other important features like canceling or removal zero sequence. Okay, we will discuss more about zero sequence cancellations later when we start to talk about overcurrent protections. Okay, here there is a very simple example about auxiliary current transformer. Here we have two CT, CT1, CT2, but in this case, I believe you can see the CT1 is 600 to 2.5, and the CT2 is 600 to 3. In this case, the primary current is 600 amps. We are doing here a very basic trick. Again, we want that the current moving across the burden is zero, and one way to use that is if we use Kirchhoff current law here in this node. But in this case, the secondary current from CT2 must be 3 amps, but also the current in this branch, I mean the secondary current on CT1 should be 3. But because the current is 2.5, we can use an auxiliary transformer in order to make the current equal to 3 amps, and then the burden be 0. Okay, what I'm trying to say is here we are using an auxiliary current transformer with transformer ratio 3 to 2.5, and the idea here is to match currents on the secondary. Okay, this is one of the applications that we can find for auxiliary current transformer. I know that people from the industry and a lot of my colleagues from protections, they will say, okay, 2.5 is not a typical secondary rate current, but this example is only for illustrative purposes. Okay, here what we need to understand is also we can use the CT in order to modify the impedance that is refer for the burden of the transformer CT1. In this case, we are installing this transformer, but we need to be careful, okay? Because the secondary will provide the 3 amps that is allowing matching the currents in this circuit and making the current across the burden 0. But you must be careful because this ideal transformer is also referring, this auxiliary transformer is also referring the impedance to and modifying the apparent impedance of CT1. And in this case, you must remember that depend of the square value of the transformer ratio, and you must take in account those kind of modifications when you are using using auxiliary current transformers. Okay, that's all with auxiliary current transformers. Now I will go about three-phase connections. You must be aware that power systems are three-phase, and when we are working in a three-phase systems, they are basically two basic connections that we can use for three-phase loads, star and delta. Well, that is happening similar to the current transformers. You can imagine here we have a classical star connection for CT transformers. Here we have the primary windings, and the secondary windings. All of them, they have a burden, and this burden is connected at star connection, and there is a common point where we are connecting the burden, and there are some impedance in series coming from the secondary of the winding to the burden. Let me try again to explain this. We have 3 2-winding current transformers. Primary is connected in series with the lines, no problem, but secondary, we have a series, we have here some series impedance, and then we are going to the burden. On the right hand side of this diagram, we have again 3 lines, we have series, but the secondary windings in this case, they are connected into a delta connection. You must remember, you must be careful using secondary connection in delta. They are a very important effect, because when you are using secondary, when you are using a delta, there is a difference between the line currents and the phase current, and this factor of square root 3 and the shifting of 30 degrees must be taken in account. It's something that I highly suggest that the students play a bit with the current calculations and the voltage across the burden when you have delta or star connection. Another important thing is that deltas and star connections, they can be used for zero sequence. As you must be aware, when we have the star connection, there is a neutral point, and in that case, every single phase burden carries phase currents. That include the positive, the negative, and the zero sequence components. However, sometimes we don't want, or we want that zero current bypass from the burdens. One very simple way to do so is, let's use again auxiliary CT transformer. That is one way that we can create a possible path for the zero sequence currents. Here, I believe you can see we have the lines with primary currents going across A, B, and C. Then we have the secondary windings, and the secondary windings we have here a star connection, but what we have done here is we have 1, 2, and 3. We have 1, 2, and 3, but those transformers, as you can see over there, they have the primary windings connect and star connection, and the secondary of those auxiliary transformers, they are connected in a delta connection. And what is the idea? Well, the neutral point of the auxiliary CT transformer, the neutral point of the auxiliary CT transformer is used to connect the neutral burden, okay? And the secondary windings of the CT in that case are providing a path for the zero sequence currents, and as consequence you will not find any zero sequence components on the borders of the phase relay. Okay, this approach is quite useful if you want that the phase relays, they don't identify or they don't have any zero sequence current moving. Okay. We will talk more about this after during the overcurrent section. Okay. Something that you must be aware is that the current transformers they can be used to take measurements of currents in a three-phase system. But what's happened if we use a Windows type current transformer, and in this Windows type or bar type current transformer, we have three currents, and in this case the three currents A, B, C, if they are totally symmetrical, the sum of the current A, B, and C should be zero. Okay, but it's the same for the fluxes. In this case, we have three currents, and the total flux should be zero, and as a consequence, the current moving for the secondary should be zero. But if we have a short circuit, and this short circuit is asymmetrical, for instance, a single phase or a phase to ground, in this case, the total current, the current A plus B plus C during the fault condition is 3 times the zero sequence. As a consequence, we can use this kind of connection in order to identify if there is any kind of zero sequence presence, or there is some sort of non-symmetrical fault in the system. Okay, sometimes the cable have some shields, and in those cases we must be extremely careful, because the shield could be grounded, and as consequence we will not get 3 times zero sequence current in this kind of measurements. Okay, because the current moving in A, B, C will be isolated or returned by the shield. Okay. Something that you must be aware is that this process that is known as flood summing, because what you are doing here essentially is you have 3 currents, you have 3 fluxes, and you use this magnetic core to perform the sum of those fluxes. What I am trying to explain is that in general sense, this magnetic core is performing this algebraic or arithmetic function, summing the 3 currents and getting the zero sequence. Okay. Well, when we have this, there are some challenges. Okay, there are some challenges. Flood summing or editing the fluxes is something that look very simple. However, you must be careful. Okay, because some applications that you require using the flux editing connection, they have very interesting problem. For instance, depending of the magnetic core design of the current transformer, you can have different performance, and that affect the possibility of the flood summing application, okay? We need to be careful about the relay sensibility, okay? Because the zero sequence components will appear when there is an imbalance, but in some applications that zero sequence can be small or bigger depending of the grounding connection of neutral points, okay? Installing these kind of transformers in order to perform the float zooming, that can be done for low power applications. I mean, if you have low voltage and you have cables with insulation, you can put 3 cables together and you can install the transformer. However, if you are working in high voltage, that is not necessarily an option. And the reason is because you need insulation, and the distances should be so big that is almost forbidden using this. Another thing is that the fluxes that are moving across the magnetic core can be affected for other fluxes. And also the flux can be affected by something that is called the leakage flux. Okay? What is happening? What is the leakage flux? Well, the leakage flux is mainly a situation where some part of the flux that is passing across the cable go beyond of the magnetic core, and as consequence you don't receive that flux in the core, and you lost some coupling between the flux and the currents. Again, this can be used for relative medium low voltage application. It's quite useful if you are working with induction motors. It's quite used this kind of approach in order that you can see some imbalance in the machine and some any kind of phenomenon that they are asymmetrical components. Okay, well, it's good that you have a reading about float zooming, and I would like to say that at this moment we are finishing the part related with current transformers. Okay, now we are moving to the next point, and the next point is the voltage transformers. Okay. Voltage transformers, in some countries they use the name PT, potential transformers. They are typically transformers designed to receive high voltage on the primary side and then transform and reduce that voltage on the secondary. Typically the secondary voltage could be 120 volts or 110 volts. Typically that is line-to-line voltage, or 69.3 if we are using 120 line-to-line voltage. Okay, this is the line to neutral, line to line voltage. Okay. Typically VT transformers, the neutral point must be connected to the neutral point. Okay, or there are some cases that we can we don't use neutral point and we keep floating the neutral point. That is the case that we are working with VTs that they are connected into open delta connection, for instance. Okay, that you want to take measurements between two different in a three-phase system, but using two voltage transformers. Okay. Something that you must be aware is that the error transformation of VT is typically very, very small, especially if you are working in a normal voltage range. Okay. However, you must be careful because in some cases, in some networks, you require that the voltage measurement should be quite accurate for bigger or greater voltage levels. Okay. What I want to say is that typical voltage transformers, they are very similar to the two-winding transformer. However, there is a limit for the application. When you start to work with extra high voltages, the classical two-winding transformer, as you know, start to be a problem, especially for insulation levels. And for that reason, we start to use what we call the